Okay, so as promised, I'm going to take up these examples where you have a graph and you have to go back to an equation. So you're basically trying your best to understand the transformations of the functions as they exist. And there's a couple of ways to do this, but most of it starts with a recognition of the type of function it is. First of all, keep in mind, this is not one function, this is two. Okay, so there's a parabola, so that's what we're going to focus on, is this parabola here. Okay, and it's on a normal xy axis. Each square is worth 1. And in this parabola, or quadratic, we recognize that, of course, our parent function is y is equal to x squared. Now that we know that y is equal to x squared, we can recognize specific points. What's happened is that the vertex, so this is the format for our base function. We've got, usually have our 5 standard points, 2, 1, 0, negative 1, negative 2. And 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, and 4. Nothing crazy, okay? The first focal point, I think, is to look at the fact that we can usually tell the vertex for a parabola. We can see it for a quadratic. So the new vertex is down at 1, 2, negative 2, comma, 1, 2, 3, 4, negative 4. Okay, negative 2, negative 4. So what's happened is that this has turned into negative 2, negative 4. Now the beauty is, especially from a quadratic, is that this point we know and this point we know has actually turned into the d value and the c value. Okay, so in other words, the vertex for any y equals x squared for y is equal to a bracket k x minus d squared, x minus d squared minus, plus c. We know that in that format, the vertex is going to be dc. It's always dc. Because what happens is when you stretch and compress the parabola that's here, it's going to get fatter, skinnier and stuff, but the vertex stays invariant. 0, 0 is invariant until you shift it. So just by looking at this vertex, we know that that's the d value and the c value. Like you did last year, you knew that was h and k. H is the same as d and c is the same thing as k was last year. So as a result, we kind of know part of the function now. We know the equation. We know d is equal to negative 2, and we know c is equal to negative 4. What we want to do after that is see if we can figure out the vertical stretch and or compression. Okay? And in order to figure out the vertical stretch and or compression, sometimes we can luck out, and if we have specific points that actually cross, like we have them, I have them already colored in here, but actually cross at nice values, then we have points to verify. But what we have to do is realize, what is that point? Well, the nice thing is that if you go over 1, okay, so from the vertex, which would be 0, you go to the right 1, or you in essence go up 1, okay, we still have the value of 1. That suggests to me that in reality what's happened is I haven't done a horizontal transformation. And you also notice that when you go to the left 1, okay, there's a point there as well, which means that this minus 1 hasn't been modified as well. So I know that this point 1, 1 has been changed. Okay, now you can go ahead and do some algebra with that, and I'll show you how to do that when we do this one. You can always use the algebra when you know the nature of the function and what point goes with what. But what you can do just by looking at it is realize that there's probably no horizontal stretch or no horizontal compression in this case. What there is usually this should be at, if I go over 1, I go up 1. So this is where the point should be here and here if this is my normal parabola, if I haven't stretched and compressed it vertically, or compressed it vertically, or horizontally for that matter. Well, now it's over 1, but instead of up 1, it's over 1 and up 3. So that means that it's been tripled. Okay, and that suggests that my a value is 3. Okay, now my k value in this case, because it looks like I haven't done any sort of value to that, then it's going to be 1. We know the parabola is right side up, so we know the a value is a negative. We can't tell if there's been a negative stretch or compression because, a negative reflection, because a negative reflection of a parabola is exactly the same parabola that you began with. So you could do either or and it won't make a difference. So now that I have all these values here, I can go ahead and I can write my equation. Again, this is for the quadratic. Okay, I'm just focusing on the quadratic. Okay, and we go y is equal to, now we put the a value where the a value is, which is 3, which is 3. We put a square bracket, I suppose. K value, we put a 1, okay? Open up your bracket and put an x, okay? Your d value is going to be minus 2. So when you substitute it in, again, you put the d value in, but there's a minus to begin with, so a minus 2. I'm going to resolve this afterwards so it looks a little bit more pretty or a little bit more appropriate or simplified. And then we have our minus 4 outside, or plus negative 4, that being the case. And then, of course, just to pretty this up a little bit, I don't even have to use these brackets anymore, because if I do a square bracket and a 1, I don't really need to do that. And minus 2 is plus 2. And then you're left with that. Okay. And that's a parabola that you probably could have figured out the equation for last year, ignoring the fact that we have a horizontal transformation factor. Okay, because often what happens is when we complete the square, we actually combine together a horizontal transformation. One thing that maybe you've realized is a vertical stretch is the same thing as a horizontal compression, roughly. Not by the same numbers, but I can make a horizontal compression look like a stretch. Just like a vertical compression, squishing it like this actually looks like a horizontal stretch. Okay, and so numerically it may not work out perfectly, but it does mean that when I am compressing vertically, I'm stretching horizontally. Okay, so that's kind of the equation of that parabola. Check. Okay, and you can always check it out if you want to by doing a mapping rule. Okay, the vertex is going to be -2, -4. Okay, it's going to be over 1, up 3, over 1, up 3, over 2, up 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So maybe it would be up here somewhere. And the same thing over here. Again, you'd have to have a bigger grid to check it out to be sure. Okay, or just substitute in a bunch of points. Okay, and there you have it. So that's the equation of the parabola. Okay, that's the quadratic. That's this guy right here. The second one, and certainly the much harder one, at least in some ways, is the reciprocal function. And that's what we're looking at here, is this reciprocal function. So this is the guy, and I can't circle it because I'm going to be circling the whole graph. Sometimes these pencils just don't agree. Okay, so that's going to be basically this function right here, and then this function right here. Okay? Now, just like before and for the quadratic, we looked for the vertex because it told me the d and the c value. For this equation, the asymptotes tell me the d and the c value. So I can see that this guy is going to approach and approach and approach. So I think that my asymptote, and I'll draw it a little bit more sort of darker just so it's easier to see. My asymptote for y is equal to 1 over x looks like it's here at y is equal to -1. And for my vertical, you're going to kind of want to sort of halfway point these 2 points that I think are the points for your base function. And also realize, hey, yeah, this approaches that. This approaches, it goes past this line. So the asymptote's not here. It's probably going to be here. And you're like, yeah, the asymptote's there. So as a result, and of course, if we zoomed out, we'd be able to see a little bit better on Desmos. Or if we plotted a few more points, it's going to be at x is equal to -3. So try to remember that that is going to be C, and that is going to be D. Okay? Now, as far as all the other points, it's a different story. Okay? What I have, remember, for my y is equal to 1 over x function, is I have the point, well, 0, and that's where my asymptote is, right? So there's no value for 0, right? It's undefined. But I have 1. Oops, maybe I should make this a little bigger. Yeah, so I can include the other points. So I have 0, and then I have -1 and 1. So 1, when I plug it into there, is 1. -1, when I plug it in there, is -1. This, of course, is no value. Okay, when I plug in 2, it becomes 0.5. Okay, because 1 over 2 is 0. I'm just going to write 0.5 because it's easier. And then -2 becomes 1 over -2, which is -0.5. Okay, so those are the points that we're looking at for your base function. The transformed function, and again, you have to look at the asymptotes because they kind of create like a new axis. And what we see is that the point that was 1, 1 is now that point. The point that was -1, -1 is now that point. Okay? So now we realize that the x value that was, when it was over here, 1, 1, and -1, -1, when we were doing our base function, has been moved diagonally. Instead of 1 and 1, it's moved diagonally 2 and 2. So it's 2 units to the right and 2 units upwards, from twice as far outwards in the x value and twice as far in the y value as it was to be originally. And originally it would be here, and now it's being double distance here, double the distance this way. And so that's going to be a very good clue to you, okay, that without using any algebraic expressions, that this is the point -1, -1. This is the point 1, 1 originally, and it's been doubled and doubled, doubled and doubled, and then it's been shifted. Okay, so we have to look at it in proximity, kind of like proximity to my vertex. My vertex for a reciprocal function is kind of the axis that's formed by the horizontal and vertical asymptotes. So it looks like I've stretched horizontally to make this from here to further out to here, and it also looks like I've stretched vertically. Stretched vertically by a factor of 2, I've doubled distances, which suggests that my a value is 2. Stretched horizontally is a little bit different. It's double the distance, but remember, a horizontal doubling is actually 1 over my k value. So 1 over k is what we actually see when we do the transformation, and I know it's a doubling. Or in other words, cross multiply, 1 equals 2k, k equals 1/2. Or you just simply say to yourself, hey, I know that when I'm doubling for a horizontal transformation, really what I'm doing is the opposite. So doubling, what's the opposite of doubling? 1/2. So my k value is going to be 1/2, and my a is going to be 2. So now when I write my equation, I'll have to write it a little smaller here, but hopefully you guys can still see. Okay? Remember that you're going to have a bracket down here. You're going to have an x here. The c value is easy. It's -1, so you're just going to put it over there. The d value is always inside the function, and it's a -3. That's a -3. Okay? Where the a value is actually usually in the numerator, and the k value, remember, is scooched right next to the x inside the function. And remember, a reciprocal function is a 1 over function or a dividing function. So my k value is going to go here. You could use 1/2 or a 0.5, although 1/2 is a little bit more appropriate. Okay? And then you use your a value of 2, and you put that in the numerator. And so I'll just clean that up a little bit. 1/2 x plus 3 minus 1. Now you may say to yourself, well, wait a minute. If I take 1/2 and I take a 2, I take a 2 divided by 1/2. These should cancel or sort of reduce. And 2 divided by 1/2 is a 4. So in other words, I could simplify this guy to this. 4 all over x plus 3 minus 1. And that would mean that there's no horizontal modification, but there is a vertical stretch by a factor of 4. So when I look here, there's going to be no horizontal. So this is where the point should be, the 1, 1 point should be. Okay, and so I times it by 4, and there's the point. Or this should be where the -1 would be, and I times it by 4, and this is where it is. Okay, so you can also do it that way if you want to use a little bit of trickery. Okay, but that's just because, if this was a bit different of a fraction, which was a little bit more, maybe it was 2/3 or something, then it would end up being, 6 over 2. Oh, that reduces to 3. Anyway, whole point is different values may not have worked out as nicely for us. But in this case, that's how you would work your way towards getting this. Now, I'm not going to say that this is not a tough one. I'm saying that maybe you're going to get like a, a quadratic, or maybe an absolute value function, right? I'll give you one over here. Or maybe I'll give you a root function, right? That'll be like there and there, and then there. And you'll be like, oh, okay. And then you can go ahead and figure that out. But at least the d and the c are relatively easy to figure out. And then you can go over 1, and what does it do? And then that's going to help a little bit, okay? But it does help to know that this point is your asymptotes, and that this point and this point are going to be key when you're looking at the reciprocal function. Okay? So that's where we find ourselves with that one. All right? It's difficult. I'm not going to lie to you. Okay? It's definitely, we're at the application phase. And I'll probably be giving you one on your test, but I'm going to be relatively civilized with what I give you, given the fact that we do have time constraints that we have here. Now I've got this scenario here. I've got the parent function, which is x, y. And then I've got the transform points, which remember is x over k plus d, comma, ay plus k. So that's the sort of the mapping rule. And I've got a point and then a final point. So I know that this point has turned into this point. Okay? I don't know what my d and my c are. All right? And I don't know what my k and my a are because I don't really know what's happened. Okay? This is 001142 is the root function. So you could actually sketch this, and from a sketch go ahead and do that. But I want to show you an algebraic approach to this. Okay? I want to show you how do we do this algebraically using this mapping rule. So what I know is that 0, 0 has turned into this thing. Now, I don't know what k is. I don't know what d is. Although if you're clever and you know the function, you do know what c. Sorry, I'm going back to my grade 10. You do know what d and c are because if you know what this point is, you know what they are. But that's neither here nor there. We can still figure it out algebraically. Maybe you don't notice it. So that's ay plus c. Okay? Oops, sorry. We don't know a and c. We don't know k and d. But we do know these values. We know these values because we take the original x and the original y and we plug into this formula and crunch out the numbers and we'll get our new x value. And we'll get our new y value. And we know that this should turn into or is equal to -4, -1. So now I know that this 0 that goes in here and this 0 that goes in here should crunch down in numbers down to -4. And I know that this part here should crunch down the numbers to -1. So it sets up this equation. I have one equation, -4 is equal to 0 over k plus d. And then over here I know that a times 0 plus c is going to equal this -1. Okay, so this guy becomes this guy, and this guy becomes this guy. Because I know what it was, I can plug in for x and y. And so I do. Now 0 over k is just 0. And so it tells me d is equal to -4. Which we could tell knowing that this is kind of the vertex of our root function. And so that's always your d and your c value. So that's d and that's c. But anyway, you can do this formula. You can do this solving equation technique. So -1, darn it. -1 is equal to a times 0 is 0 plus c, which is just c. And c is equal to -1. Okay, so now we have something to go by. Now we know, okay, that my original formula, so now we know x, y transforms to, still don't know k, but we know plus c is -4, comma, and then we know the -1 as well. So we don't know a, but we do know c is a -1. Okay? Now, what we do is kind of the same thing that we did before, but we take another point. And we are given 3 points. Sometimes you only need 2, depending on what you're given. Okay? But we are given 3 points. So I'm going to take this point 1, 1. I'm going to do exactly the same thing. I'm going to say 1, comma 1. But the difference is I'm going to go blank over k, because we know the x value. That's where the 1 goes. But for the plus d, I'm going to use the -4 that I just figured out, because I know more about it. I'm going to use for the blank times, for a times y, a times the blank, which is where I'm going to put the y value in here, okay? But I'm also going to know that c is -1, and so I'm going to put the -1 in there as well. So now it's not d and c, now it's -4 and -1, okay? And I know that that point turns into, 1, 1 turns into -3.5, and I'm going to use decimals here because it's easier, and -4. So from that, maybe I can figure it out algebraically. Okay? So I take my 1 and I plug it in for x, and I take my 1 and I plug it in for y. And so what I'm left with is an equation here. Negative 3.5 is equal to 1 over k minus 4. For this guy, I'm going to have negative 4, that's this, is equal to, this is a little easier, a times 1 minus 1. I'll do that one first. A minus 1 equals negative 4. A, bring it over to the other side, is equal to negative 5. Okay? Oh, sorry, negative 3. No, yeah, negative 3. A negative 4 plus 1, which is a negative 3. Bad, Mr. Henley. Okay? So what I've done basically is I've tripled my points normally. And then, of course, I've also shifted it. So it's a bit cryptic. You've hit it a little bit. Okay? I'll go ahead and solve this one. This one's a little bit more complicated. What you need to do is get the k out of the denominator, right? So you multiply everybody by k. 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 So I'll draw it out here. Negative 3.5k. K times 1 over k. So negative 3.5 times k. K times 1 over k minus 4 times k. Okay. K's cancel out there. I'm left with a 1 minus 4k is equal to negative 3.5k. And you've got to collect the k's. I should move that up a little bit. Oh, I don't even know if that was in the field of view. Oh, I'm sorry. I'm solving this equation. So I multiply everybody by k. So I multiply this term by k, this term by k, this term by k. I do it so that the k's cancel out. Okay, the k's cancel out in this fraction part. And now we've got k's only in the numerator, and then we've got a constant 1. Okay? Bring the 4k over here, so it becomes 4k minus 3.5k equals 1. 0.5k equals 1. K is equal to 1 over 0.5, or 2. So we get a k value of 2. All right? Now, we probably should look at this a little bit more carefully to make sure that we did it right. One thing that's kind of interesting in all of this is that my y values, maybe I should sketch it so we can see it a little better. Okay, so I'll do a little sketch of this just to see if it matches with our equation, just to see. You can also put it on Desmos. Okay, plot the points on Desmos. You can put it in a table the same way. 1, 2, 3, 4, 2, 3, 4. 1, 2, 3, 4. So I'll plot negative 4. Oops, sorry. 1, 2, 3, 4. Negative 4, negative 1, which is this right here. And then I'll go negative 3. Negative 3, 1, 3.5, and negative 4. So negative 3.5 is here, and negative 4, which is down here. Oops, and I got to keep going down. 1, 2, 3. And then I've got negative 2, negative 7. This is there. 3.5. 1, 2, 3, 1. And so there you go. So there's our function. It really almost looks like a straight line. Okay, and again, I haven't done this perfectly. Okay, but either way, it is what it is. So if you look at this function, what has happened? Well, the normal function looks like this. Okay, so certainly it's flipped upside down. So it looks like that, right? Then it's probably been stretched vertically, okay, to look more like that. Oh, sorry, I should draw it. Doesn't really look very good, but anyway. Maybe I should have done this in normal grid paper, but it is what it is. It's definitely been stretched vertically because you can see this positioning, this compared to this. It's definitely been stretched vertically, and by a fair bit, actually. Okay, we go over 1. It looks like we go up 3. Okay, and that's good. And then what we've done is once we've stretched it vertically, we could have compressed it. In this case, it's actually stretched outwards a little bit, so it's more like that. And then we move it 1, 2, 3, 4 units this way and down that way. So this turns into this, which is good. And then this point right here, which is probably going to be here, probably going to be here-ish. But it's not, maybe it's not exactly this value. Again, it's just a sketch. So I'm going to go over 1, 2, 3, 4, and then go down 1. And so it should be roughly on here. But again, this is a sketch. And then the same idea for this one over 4. Sorry, for this one over 4, down 1. Okay, and we should get this function. So it does look like we've done it the way that we should be doing it. Now, I haven't written out the final equation, okay? But I do have a d value of negative 4, a c value of negative 1, a value of negative 3, and a k value of 2. So when I write this final equation, and I'll just write it down here, okay? Remember, it's going to be a root function, so y is equal to, I need that square root sign. I need a bracket inside that square root sign. So my c is going to go out here at minus 1. My a is going to go up front here at negative 3. My k is going to go over here at 2. And then my d value is going to be x minus minus 4, or negative 3 to x plus 4 minus 1. I'll just have to close off my square root. And so that function really does look like what's been graphed. But that's how you do it algebraically, given that you know what the old point is and what the new point is. Now, we could have done that. We could have done that for this one and for this one. But a lot of people, the algebra is a little bit more complex, and so people find it a little bit more difficult. Now, these are very difficult to do. I'm probably going to ask you either one of these, or maybe both. Okay? But the whole point is that is an expectation that we should be able to go from equation to graph. Okay? From graph to table of values. From table of values to equation. From table of values to a graph, which is easy. You just plot the points and connect the dots. And we should be able to go from equation to table of values. Just plug it in, substitute, and get some values. And we should be able to go from graph to equation. Okay, so we need to be able to interchange all of these. If you can do that effectively, then you're in 1,000% awesome shape. I will tell you that if I do ask you to go from a graph to an equation, I'm going to be gentle-ish with you. Or a table of values to an equation, I'm going to be gentle-ish with you and probably use whole numbers and stuff just to make your algebra a little bit easier. Okay, the table of values to equations especially. The graph to equations, I'll make it something that's a little bit more obvious of a function. I may steer away from the root function. Doesn't mean you don't need to know it, because next year you'll definitely need to know it. Okay? So that's where we're at, and that's where we're going. And if you can do that, you totally get everything more or less in this unit. So good for you. Or at least you get all the transformations. So well done. Bye-bye.